Thank you for joining us as we try to go over water. Now, my goal here is to try to help make you wonder and think about all these special properties of water, really to kind of put those CK12 textbook problems into context while you're doing your schoolwork from home. So keep in mind that as we study water, please remember how to measure temperature. Fahrenheit, Celsius, Kelvin. Please remember how to measure pressure, PSI, or atmospheres, are probably some of the ones that we've heard of or used the most. Now, Celsius's temperature scale is based on water. 0 is the freezing point, and 100 is the boiling point. 0 is also considered the melting point, and 100 would also be the condensing point, and that is in Celsius. But Fahrenheit's really just kind of based on human experience. 0 was about as cold as they thought it was possible at the time that Fahrenheit invented his thermometer. And 100 is what they thought was pretty hot outside at the time he invented his thermometer. And then Kelvin, as we've discussed, is based on that absolute 0 scale, where at 0 Kelvin, all molecules stop moving. Okay. All right, now what makes water so special? Last week we did literally look at what makes ice float, or different ways to graph the phase changes of water using pressures and temperatures. But we do remember how ice will float in water. Liquid water is incompressible. In other words, liquid for water is the most dense phase. It takes a long time to heat up water. That's what high specific heat capacity means. It also takes a relatively long time for water to cool down. And the other thing, and we'll look at here a little bit, is that water really has these strong cohesive forces. Really stronger than a lot of other liquids. Okay, but one thing that fascinates me is how can water, I mean here we are, this is down in Lesterville near the Black River, but here we have liquid water. I could have a cup of ice sitting with me there. There's obviously water vapor, you can see a lot of the fog there. But yeah, to me it's interesting, like how can water, how can it be all three phases right now? I mean, I could sit here and have a little cup of water. There's ice, there's liquid, and obviously there's vapor. There's steam, if you will, in the atmosphere. There's another phase of matter called plasma, but we really won't deal with that here. Plasma is more refers to like what the sun is, or I guess what a lightsaber is, but that's just kind of a made-up thing. Okay. All right, so water, we know solid to liquid, and liquid to solid, those phase changes happen at the same temperature. Liquid to gas, gas to liquid, those phase changes happen at this temperature. And then sublimation and depositing. Depositing is a gas just dropping right out and switching right to solid. And that can happen at a lot of different temperatures, but really all of these kind of depend upon what the temperature of the surroundings would be too when the phase change happens. So phase changes not only depend on temperature, but they also depend on pressure changes. So let's go ahead and real quickly here watch water go through all three phases. So the video is a little skippy, but there we go, ice. And then that ice, it melts really quick. It's time-lapsed. The boiling takes the longest part. Boiling does take more energy and more time than melting. Now, that salt that was left behind from just melting and boiling those ice cubes, we'll talk about some of that salt, but a lot of that was already dissolved in there. Kind of weird. But remember, with those phase changes you saw, basically we just increased the temperature of water. So if we were at room pressure, water started as a solid, and it kept heating, changed to a liquid, kept heating, changed to a gas. So once again, really all we did on that phase diagram is we just kind of blew right through all of water's phases. It was a solid, it was a liquid, then it turned to a gas. So we just moved really horizontally across this phase diagram. Now, what makes water special, remember, is that its phase diagram is different than all other stuff. I mean, honestly, I could have probably thrown dry ice in there, and it would have been similar if we were at the right pressure. We could have just gone solid, liquid, gas. Same with the water, solid, liquid, gas as that temperature increased. But remember, really what makes water unique and special and makes its properties different is when I pressurize, so I got solid ice, I pressurize it. If I squeeze it, I move from the solid into the liquid portion. So remember, when you pressurize ice, you liquefy it, you melt it, you move into the liquid range. And that's really why liquid water floats. But that really also, remember, is what makes life possible. So there's a nice picture of the moon, no life on the moon. Nice picture of Earth, there is life on Earth. All right, some other properties of water that make it very special. We take it for granted that it's just like if I stick a paper towel in a cup of water, the water's just going to rise on up the paper tube, up the paper towel, up the plant, if you will, up the plant material. So we just really take that for granted that that happens. But in some ways, it's pretty special. I mean, capillary action rising up the paper towel like that, it is in some ways defying gravity. So yeah, if you just, I don't know if you've ever tried, you just stick a paper towel, like this is like a melted wax from a candle. No, nothing. It's not going to do anything. But if I obviously did it with the water, it does start to rise up the tube there. So yeah, here, it's just something you can play with at home. But once again, we take it for granted because it just happens all the time. But wax would not do that. Grease would not do that. Grease would not. Holy cow, look at that. Oh, wow. So grease wouldn't do that. All right, water's the only thing that's going to rise up like that. All right, capillary action. Water will defy gravity and rise up the plant. All right, some more evidence that water sticks together well. It's just kind of watching to see what it does. Now, this is second grade type stuff. But I thought it might be fun. Gosh, I couldn't even read the dates on my pennies. Sorry, class. All right, so what am I going to do? I'm going to say that the steel, iron, should not float. But in fact, paper clips do not float, but they can rest on the surface. Okay, so this is just some more evidence of how water sticks together. Here's my little, I'm just going to pour a cup of water. Once again, it's things we take for granted, things you've seen all the time. Oh, I'm going to spill it. Oh, I'm going to spill it. Okay, that's really cool that water sticks over the edge like that. Why isn't it falling down? I don't know, we just kind of take it for granted that it sticks together like that, but it does. In fact, it sticks together so well at the surface that something that's like almost 8 times as dense can just sit on the surface. Holy cow. I don't know. So I think it's really, like I said, we probably take it for granted, and you may have tried to do this in second grade. But yeah, but water's really the only things that could do that. Rubbing alcohol won't do that. Grease, oil won't do that. Fingernail polish remover, acetone won't do that. So yeah, water is really one of the only things that allows that surface tension to really overcome things that are a lot more dense than it. Maybe you've tried this too. It's those actual answer activities we were going to do. But once again, it's just silly, but you're just dropping water on a penny, but you can still get that same big bulb, if you will, that big kind of all that water stick together on the surface there. And you can really get a pretty big drop of water to sit on the head of your penny. But then I don't know, it's kind of cool how it sticks to my finger. So just when water sticks to itself, that's called cohesion. When water sticks to something else, that is called adhesion. And once again, it's just stronger than other chemicals. So like rubbing alcohol. Now I can get a little bit of it to kind of like sit over the edge, but that's a solution. There's like half of that is water, really. But yeah, but still, just with that alcohol in there, it breaks up that surface tension and does not allow those paper clips to sit on the surface like just regular water could. And then same thing if I were going to go to try to put some drops on a penny, those would not spill. And once again, all those paper clips floated to the bottom. If I tried to put some drops on a penny, they would not do so well. Yeah, same thing here. I mean, this is, I just look at it being silly, but I'm just looking for things I had at home. Here's some acetone. All right, now acetone will not mix with water. It won't blend with water. So this is fingernail polish remover. Hopefully it won't take the finish off of my table. Wasn't really thinking there. But yeah, I can put a few drops on the penny, but then they start to spill. I can't get nearly that same size of a big bowl there, all those giant drops. So the acetone does not have as strong a surface tension as water. It won't have that same capillary action, won't have that same surface tension, does not have as strong as adhesive qualities as water. Okay, so making these solutions. So what is a solution? I always just think you're going to take something, solute. Now your solute we generally think of as a solid, like some kind of salt or something, but it could be liquids, right? That rubbing alcohol was a solution with alcohol solute. Most of the time, water will be our solvent. If the stuff is going to blend or mix with water, it will have to be polar. Remember, likes dissolve likes. So if we get it to dissolve in water, we call it an aqueous solution. Acids and bases are aqueous solutions. Now, how much stuff you can dump into your solution is really what determines how saturated or how concentrated your solution will be. I think we know if we cook things, we get them hot, you can dump more solid in there. And we'll kind of look at this a little later, but gas actually decreases the solubility. So if you in other words, if you have carbon dioxide dissolved into a can of soda and you heat it up, the carbon dioxide gets out of solution. But if you have a beaker of salt water and heat it up, you can dump more salt in. You increase that solubility. Really, think about making crystals. All right, I really wish we had our crystals. Oh, I miss our classroom. But yeah, we made copper sulfate crystals. We dumped copper sulfate into a solution of water. And then really as the water evaporated, we were left with the solid crystals left behind. But yeah, we made a solution of copper sulfate in class. We dumped salt into the solvent. Copper sulfate is polar, so it dissolved in a polar material like water. Salts. I like to think of salts as being superpolar. Salts will dissolve. Things that dissolve well, often we can call them strong electrolyte. So once again, just kind of think about some of the things we played around with in class. If we got it to dissolve and it was a strong electrolyte, we could put a little light bulb in there. Remember, we would put the solution and the light bulb would glow. Or if it didn't dissolve or didn't conduct electricity when it was in there, the light bulb would not glow, would not turn on. So we called them a non-electrolyte. Most ionic salts are strong electrolytes. Now, things that are nonpolar are not nonpolar. Not remember, salts are ionic. Nonpolar would be like our grease, our fat. The acetone is nonpolar. These will not form a solution when mixed with water. All right, so these do not mix. Likes dissolve likes. These are examples of non-polar materials. Oil, acetone. Okay. Now once again, if they do dissolve, a lot of times they're considered a strong electrolyte. Now, how much stuff you can actually dump in, so how much solute you can get into your solution, is a measure of how concentrated it is. Now, we will measure concentration in units called molarity. Molarity is the moles you dump in divided by the liters of solution. So moles divided by liters is molarity. And it's really just a measure of how many particles, how much stuff you dumped in. That's all that's a measure of. Let's look at a few examples, and this will help us as we look at acids and base solutions next week. So let's just say I'm making a solution. I dump in 2 moles of HCl in 1 liter of solution. That is a concentration of 2. 2 molar, the molarity is 2. Now what if I took 2 moles of that hydrochloric and dumped it in 2 liters of solution? Well, now I have 2 moles divided by 2 liters. It's a 1 molar solution. 1 is the molarity. What if I took those same 2 liters and dumped them in half a liter? Well, then I would have 2 moles divided by half a liter, and that would actually be more concentrated, or a concentration of 4. So yes, so next week we will really focus on looking at these solutes that we dump into the solvent. How concentrated are they? And then will also help us decide if these acids or bases. Thank you for joining us. I really look forward to everything. Ooh, remember our soap too. I miss our classroom. I wish our soap was still there. Okay. Okay, well, hopefully maybe you had your soap. But remember, the soap would be both polar and non-polar. It can mix with both. But sometimes there was that greasy oil, that greasy layer that maybe didn't dissolve or didn't get in there. So that wouldn't dissolve with the water. Okay, but yeah, maybe just remember the soap. Remember the soap to think about polar and non-polar, making that. But once again, thank you for your time. We will review concentrations again next week. Thanks for listening.